Have you noticed how machine learning is appearing almost everywhere in hydrology these days? They are becoming increasingly common in rainfall runoff modeling, streamflow forecasting, and flood prediction. But what exactly is machine learning? Why has it gained so much attention in hydrology? Are they going to replace conventional models? And with so many available algorithms, how do you know which one is suitable for your application? In this video, I will provide a practical overview of machine learning techniques in rainfall runoff modeling, discuss their strengths and limitations, review some of the most commonly used algorithms, and finish with a few best practice recommendations for model development and algorithm selection. Let's get started. Traditionally, rainfall runoff modeling has relied on process-based models. These models aim to represent hydrological processes such as infiltration, evapotranspiration, soil moisture storage, and routing using mathematical equations and conceptual representations. Machine learning takes a different approach. Instead of explicitly describing physical processes, machine learning algorithms learn the relationship between inputs and outputs directly from historical data. In a rainfall runoff application, the model receives information such as rainfall, temperature, antecedent conditions, and catchment characteristics, and learns how these variables relate to stream flow observations. In simple terms, rather than telling the model how the catchment works, we let it discover patterns in the data itself. There are several reasons why machine learning has attracted significant attention in hydrology. First, rainfall runoff processes are highly nonlinear. Machine learning algorithms are particularly effective at capturing these complex nonlinear relationships. Second, we now have access to far larger datasets than ever before. Long-term monitoring records, remote sensing products, radar rainfall estimates, and climate reanalysis datasets provide enormous volumes of information that machine learning methods can exploit. Third, hydrological systems possess memory. Streamflow today depends not only on current rainfall, but also on what happens days, weeks, or even months earlier. Certain machine learning architectures are specifically designed to capture these temporal dependencies. Finally, machine learning models can often be applied across multiple catchments with minimal manual calibration, making them attractive for larger-scale forecasting in ungauged basins. However, it is important to recognize that machine learning is not replacing hydrological science. Increasingly, the focus is shifting towards hybrid approaches that combine physical understanding with data-driven learning. Although dozens of machine learning algorithms exist, most rainfall runoff applications can be grouped into four broad categories, each with its own strengths, limitations, and the areas of application. Let's go through them. The first group are neural networks. They are inspired by the structure of human brain and consist of interconnected processing units called neurons. Their ability to learn highly nonlinear relationships makes them one of the most widely used machine learning approaches in modern hydrology. The simplest form is the artificial neural network, or ANN, which has been used in rainfall runoff modeling for several decades. As datasets have become larger, deeper architectures have emerged. Deep neural networks, or DNNs, use multiple hidden layers to learn increasingly complex patterns from large datasets. For time series applications, recurrent neural networks and particularly long short-term memory networks, or LSTMs, have become highly popular. Their memory structure allows them to capture temporal dependencies, antecedent moisture conditions, recession behavior, and delayed catchment responses. This makes LSTMs particularly effective for continuous rainfall runoff simulation and streamflow forecasting. A closely related architecture is gated recurrent unit, or GRU. They are generally simpler and computationally more efficient than LSTM, while often achieving similar predictive performance. They can be attractive when computational resources are limited or when rapid model development is required. Another important architecture is the convolutional neural network, or CNN. They are designed to identify spatial patterns and are particularly useful for radar rainfall data, satellite imagery, gridded climate datasets, or spatially distributed catchment information. The second group are tree-based methods. These algorithms make predictions by repeatedly dividing data into smaller groups based on decision rules. Modern implementations combine many decision trees together to improve robustness and predictive performance. To Two of the most popular examples are Random Forest and XGBoost. Random Forest builds a large collection of decision trees and averages their predictions. It is relatively easy to implement, robust to noisy data, and provides useful information about the relative importance of different input variables. XGBoost, on the other hand, takes a different approach by building trees sequentially, with each tree attempting to correct errors made by previous trees. This often results in excellent predictive accuracy, and GBoost has consistently performed well in comparative rainfall runoff studies. For many practical hydrological applications, Random Forest and XGBoost remain among the strongest alternatives to deep learning models. Next are kernel-based methods. These algorithms attempt to transform data into higher dimensional spaces where complex relationships become easier to model. These methods are particularly useful when datasets are relatively small, but nonlinear relationships are still important. The most widely used example is the support vector machine, or SVM. Another important method is Gaussian process regression, or GPR. In addition to providing predictions, GPR can estimate prediction uncertainty, which is often valuable for risk-based decision-making. However, computational demands increase rapidly as the dataset size grows. Lastly, Neuro-Fuzzy systems. These methods represent hydrological relationships using linguistic rules rather than purely mathematical equations. The simplest form is the fuzzy inference system, or FIS, which uses expert-defined if-then rules to represent catchment behavior. A more advanced approach is the adaptive network-based fuzzy inference system, or ANFIS, which combines fuzzy logic with neural network learning. ANFIS can automatically adjust membership functions and rules based on observed data while still retaining some level of interpretability. These methods are particularly useful when expert knowledge is available or when model transparency and interpretability are important. Before moving on, it's important to mention a class of techniques which are often discussed alongside machine learning but serve a different purpose. I'm referring to bio-inspired optimization algorithms. Let's explore them. Bio-inspired algorithms are generally not used as rainfall runoff models themselves. Instead, these optimization techniques are integrated with machine learning models to optimize model parameters, network architectures, and hyperparameters, thereby improving predictive performance and reducing calibration effort. Examples include genetic algorithms, which mimic natural evolution, particle swarm optimization, which is inspired by the collective behavior of bird flocks and fish schools, and ant colony optimization, which emulates the pathfinding behavior of ant colonies. Despite their success, machine learning algorithms are not without limitations. Let's know more about that. Perhaps the most common criticism is their lack of physical interpretability. A model may produce excellent predictions while providing little insight into why those predictions occur. Machine learning models also struggle with extrapolation. If future conditions differ significantly from the historical training data, performance can deteriorate rapidly. Also, many algorithms require large quantities of high-quality data, and uncertainty estimation remains a challenging area of research. This highlights an important point. A highly accurate model is not necessarily a reliable one if its limitations are poorly understood. A common question is, which algorithm should I use? The answer depends on the problem. You can refer to the following table for algorithm selection. The key is to match the complexity of the algorithm to the complexity of the problem, rather than automatically selecting the most sophisticated model available. Regardless of the algorithm chosen, several principles remain essential. Focus first on data quality. Poor data will undermine even the most advanced machine learning model. Use appropriate temporal data splits for training, validation, and testing. Always compare against simpler baseline models. If a complex deep learning model cannot significantly outperform a simpler alternative, the added complexity may not be justified. Finally, evaluate performance across different flow regimes, seasons, and extreme events, and never rely on a single performance metric. As machine learning continues to evolve, the future of hydrological modeling will likely involve closer integration between data-driven techniques and traditional process-based models. Thank you for watching. If you found this video helpful, please share your thoughts and experiences in the comments below. I look forward to seeing you in the next video.